thank you everyone for being here, for waking up so early today. On behalf of myself and my co-authors, Mohammad, Fadiheh, Johannes, Müller, Lena, Duque, Antón, and Professors Dominik, Stoffel, and Wolfgang Kunz, I would like to talk about a methodology that we have developed that allows us to design access control mechanisms in systems on chips with formal integrity guarantees. So first, a bit of a background. We are witnessing an ever-increasing need for SoCs with diversified hardware. Based on the purpose of the SoC, the system integrators will insert various specific hardware components, crypto engines, neural network accelerators, customized, optimized communication protocol implementations, etc. But more often than not, they will not design these components themselves, but they will outsource it to other companies. And then they will integrate their designs into their systems. The problem that might arise with that is if they do not fully trust these companies, then they might have issues, trust issues with these third-party IPs. So not only do you have to worry about trusted and untrusted software running on your system, but you might have to worry about parts of your chip being less trusted than other parts. And this is sort of the main idea of our threat model. So on the right, you have a basic SoC model. You have your controllers on the left, peripherals on the right, an interconnect in between through which they communicate. But most importantly, we have to notice that this SoC's hardware is divided into two domains. Essentially, a high security, fully trusted domain and a less trusted, low security domain. And it's also equipped with a hardware access control mechanism, which ensures that the communication between those domains will not endanger the security of the high security domain. So it's data and operations running on it. And as the session name suggests, we worry here about integrity. Specifically, we're assuming that on the high security domain, we have some security critical operation going on, which we don't want it to be tampered with. So we can express our security target as an information flow restriction and basically say that the low security domain should not in any way influence the visible behavior of the high security domain as seen through its primary outputs. And expressing security targets this way as information flow restrictions is neat for us because for a few years now we've been developing a verification methodology called UPEC, which stands for Unique Program Execution Checking. And UPEC basically allows us to exhaustively verify exactly this type of information flow restrictions at the register transfer level. And the way it does that is it uses a formal verification technique called interval property checking. Now, long story short, interval property checking expresses the SoC as a logical model and compares it to a set of properties, behavioral properties, and if there is any state or any configuration of our circuit that violates the property, it gives a counterexample. So UPEC uses this and uses not one, but two instances of our SoC or of any sort of circuit to express security properties, which in turn express these information flow restrictions. So for our case, for operation integrity, that would look something like this. So the properties standard format is that of assumptions and commitments. The assumptions, the basic idea is if the circuit fulfills the assumptions of the property, it also has to fulfill the commitments. Otherwise, the property fails. So for UPEC, or UPEC for operation integrity, the assumptions look like this. We basically assume that at the beginning, the microarchitectural internal state of the high security domain in both instances is identical. It can be anything, but it's the same. We also assume that both instances are fed the same inputs, which means throughout the whole duration of the properties, which means that the only difference in the beginning is the low security domain, its internal state. And we also assume that throughout the duration of the property, the access control, which is supposed to protect this security, is properly configured and activated. So then The commitment says that after some time interval k, the secure outputs in both instances are still the same. If the property is broken, if they're not the same, that means the difference is propagated from the low security domain to the high security domain. The problem here is that the property is bounded by this time interval k. So then the natural question arises, how long does k need to be? And unfortunately, the answer is it needs to be very long. In fact, too long for formal checkers to just run this property once and have a pass or fail. So we have to give up on that, but instead decompose our verification target into smaller properties, which when we run in a certain defined way, we still get the global security guarantee. So the first step towards that is to add another commitment to our property. We now look not only at the outputs of the high security domain, we also look at its internal microarchitectural state in the commitments as well. And what does that allow us? Well, here's the MITRE model in the beginning of the property at t0, the initial time. The red color signifies the parts of the circuit that are different in the two instances. And now for some short interval k, we can get a counterexample from our formal tool, which says that some internal state of the high security domain has been affected. Not the visible behavior yet, but it is something that we call a P alert or a propagation alert. We basically have to record what has happened and then use this situation, this scenario, to assume these differences in the next iteration of our property and see whether for some additional time interval, it will eventually propagate to the outputs. And if it does, then we have what's called a T alert, and that's the proper integrity violation as we've defined it. So using this basic idea, we developed a verification methodology which gives global guarantees. It is induction-based, which means it consists of two primary parts. The main goal of the base proof is to verify operation integrity for a bounded time window k and to find all of these P alerts that might occur. And it finds all of them exhaustively. The step proof then uses these as assumptions and sees, thanks to the exhaustive nature of interval property checking, they see whether at any point in the future these could eventually evolve into T alerts. Also, while designing the verification methodology, we've added some additional optimizations to make the proof more scalable. Most importantly, a technique to perform sound black boxing, basically abstracting away the pieces of the circuit that are not relevant at the moment as we follow this propagation through. And then using this verification methodology, we have proposed a design flow which uses UPEC-OI as the thing that tells us whether our access control is completely secure or not. We performed a case study on OpenTitan, an open source SoC, which is meant to be a root of trust. So it doesn't fully add to our threat model because all the IPs in OpenTitan are built in-house and extra care is taken about security, but it's open source, so we added some malicious IPs to model the threat. And we designed an access control mechanisms ourselves to protect the rest of the circuit from these threats. And then we use the design flow and UPEC-OI to see whether our access control really does the trick. And the results are more detailed in the paper, but here's a short summary. Based on our design, we had to iterate through this process 19 times. However, an average property check time throughout this whole process would be around 5 minutes before we would get a counterexample and say, you have a leakage here or there. Once we've gotten rid of all the bugs and ran UPEC-OI for one last time, the longest time it took for it to fully verify the integrity is 11 hours. And throughout this time, the peak memory consumption was 25 gigabytes, which is for a work desktop computer, it's applicable. And for reference, the design size was around 14 million state bits. So in conclusion, we've developed a methodology to formally verify operation integrity. The paper talks in details about how the property is formulated, how it's decomposed, all these other optimizations we've done. And we then, in our case study, use this methodology as the key point in our design flow to equip a realistic system on chip with access control. And yeah, that's a short summary of our work. Thank you, and if you have any questions, I'd be happy to take them.